it's a chance to like give feedback right away. Start right at the beginning. All right. So this week is all devoted to neural networks. Raise your hand if you've heard this term outside of this class. All right. What have you heard before stepping into this class? What did you think a neural network was? Where had you heard the term before? Ned?
It didn't have anything to do with computers. I took I took a neuroscience class in high school, and like the neural network and like synapses and stuff like that. That was the only time I heard.
Yeah, and we touched on that quite a bit with the perceptron in the beginning of the semester. Yeah. We're going to, of course, cover it again today. Where else have we heard about neural networks? Psychology? Okay. But were you aware before this class that that's a lot of the technologies underpinning like quant analysis and kind of this whole movement of deep learning? Or is that just completely new? Okay.
Roughly kind of AI.
Roughly kind of AI. I think that's a fair, yeah, it's AI-ish, right? These aren't technically the algorithms that like ChatGPT uses. Those are transformer networks, and we're going to talk about those after we cover neural networks. But this is the start of like the AI revolution, is when people started to be able to use this kind of structure rather than things like just a perceptron or support vector machines, or more like statistical analysis like PCA, or kind of clustering unsupervised or supervised algorithms like k-nearest neighbors. Those algorithms have been around for a while, and really it wasn't until we got the processing power to be able to do something called backpropagation that we were able to actually start using neural networks. So the first inklings of a neural network go all the way back to like the 50s, DARPA, Marvin Minsky, Rosenblatt, the perceptron, which we've covered. And then we went through this huge thing called an AI winter, where basically we didn't have the computational abilities to do the stuff we're going to talk about today. So it wasn't until like the early 2000s, late 90s, that people started being able to pick up the perceptron and run with it and do some pretty amazing things. I think that's interesting on some level, that theoretically people knew that this was probably possible, but there was just no way to do it. I think like Da Vinci did a lot of that too, like invent things that were way ahead of his time, and then we just kind of had to wait for them to come into motion. So before, especially since we're coming back from spring break, before we jump into this, we need to do a little bit of review. The image is a matrix of light. Remember, your pixel values are going to be normalized intensities of this light, ranging from like 0, 1 or 0 to 255. This should be review from the exam. But today you can use neural networks for a lot of different things. We're going to use them for image classification because I think that one, it's something I'm really interested in, and two, I think it's very easy to think about an image rather than it is to think about like a tabular data set that has economic data in it. Does that make sense? So we have these pixels here for a color image. How many channels do we have? 3. Okay. And how would we compute an edge here? This is like review from the midterm exam you just taught. Yeah, the change in gradient, right? And it's like pretty easy to see here. Oh, this doesn't work anymore. That you'd have a pretty big change in gradient here from light parts to the dark parts of the image. So feel pretty confident here? 55, 5 is good? All right. And then we also talked about convolutions or cross correlations. It doesn't matter what you call those. And we talked about the root of that takes place at the kernel level, right? And so a kernel is just a small sliding window that goes over. And here we have a Laplacian that's convoluting over that image. And it's giving us basically the edges of the image, right? And so we're pretty comfortable with the concepts of the image as a mathematical function that takes 3D real-world space, converts it to a 2D plane in which there are pixels, which are matrices of light, and we have filters that convolute over an image to provide some new information. Feel pretty good? I'll review. And then we looked at some common kernels. These were, I think during the midterm exam, I wanted you to like remember 3 of them, and many of us got 2 right away. And for some reason, resizing was one that people had a lot of trouble with. Edge detection, blurring, resizing, sharpening, and then the Sobel X and Y are just edge detection in different directions, right? What is a corner? Where two edges come together. There we go. We talked about sometimes we're representing these kind of problems in a new dimensional space, right? I think before we had covered some of the machine learning stuff, this might have been a little crazy. And now after we know about support vector machines, PCAs, I think the concept of playing with dimensionality should be a little more comfortable, right? That will often go into different dimensions to solve for a problem. For example, with edge detection, once you add a different dimension, once you go into a third dimension, it becomes really easy to see where the edges are. There are these cliffs, right? And so you can think about it as like you're setting out like a series of, I don't know, warning signs before you drop off the cliff. Does SVMs reduce dimensionality or expand dimensionality? Yes, it expands it. It often goes into different dimensions to solve it. Remember, this is the paper thing where we can take a one-dimensional space that isn't linearly separable and then solve it in two dimensions. All right, looking at more just kernels and convolutions. Why do you think I'm hitting this so hard before we jump into the new content?
Make sure we know it.
Yeah, because it might be crucial to what we're going to cover today, right? And then we looked at some features. Here, now all this works all of a sudden. Some features are probably more important than others, right? Whereas edge was pretty important. This is straight from the midterm as well. A corner is even more important because, as John says, it's where it comes together. So if it comes together, that might be a more important feature. And what we're going to look at today is how do these algorithms begin to pick out the important features in an image based on a training data set so they can go back and have like some real life memory that can always detect that baseball cap or that dog or that salmon or, you know, a bottle of ketchup at the grocery store, right? And how we're going to do this is we're going to take small regions of interest and group them together in important features, and then that network is going to learn which features are the most important. So would you call neural networks low, medium, or high level computer vision? It's definitely not low. Medium is usually grouping features together, but what we're going to see, this is kind of a trick question because we haven't looked at some examples yet. We're going to see that oftentimes this allows us to get to a semantic understanding of the image, right? And so that would probably be high. Then we talked about corner detection. So this is great. We're picking out, we're grouping features. I think this is a good medium computer vision level. And we're basically saying that when it comes to this image, these are the features that make it unique, right? And we spent a lot of time talking about different ways that we can match corners together for things like making maps or stitching images together for panoramas. And after we did that, we discussed kind of, well, how do we use this like to solve problems? We have this general scientific process in which we're going to have a hypothesis. We're going to throw an algorithm at it to try to solve it. We're going to measure the error. We're going to try to reduce the error, and we're going to do that throughout the entire thing by splitting the data into a test, train, and validation data set. Does this all sound good? Fist of 5? We feeling pretty good? Let me see where you're at. All right. And we talked about parametric and non-parametric data sets. Can anybody remind me what the difference between these two are? And it's fine if you just read them directly off the slide. So we looked at k nearest neighbors is a type of algorithm like this because it has to go through every point in the data set in order to make a new interpretation, right? And SVMs are like more of these kind because you don't do that. You find a best fit line. Does that make sense? Just keep that in the back of your head. All right, so let's start. with the final piece of review here, which was the perceptron, which I think we're probably pretty comfortable with. It was on the midterm. Remember, I told you, we've seen this slide a lot, that way back in the 50s, under a DARPA project, a lot of people were really interested in taking the understanding that we had of the human brain and mapping that onto an artificial mathematical neuron, right? The same idea here was that just like in a cell, when inputs come in, these would be our inputs, we're going to multiply them by certain weights. And if the weights, the sum of the weights times the inputs plus the bias term is larger than the, gives us a value that's larger than our activation function, we're going to fire, right? Just like a neuron in the brain fires across the axon terminal if that impulse reaches the activation function. So it might be like a motor neuron or a pain neuron, right? It's told to fire once you reach a certain threshold. Put your hand over a stove. Once you hit the activation function, it hurts. This is basically the same idea, right? And what did we learn about the perceptron? What's it good at? What's it not good at? What are some of the problems or benefits of it? Ned.
It's good, like it can find a line, of classification,
Mm-hmm.
but it's not like it does all the different lines. It's not the best one.
Absolutely, yeah. So it's trying to basically figure out what the weights are as a machine learning model. We looked at an example of this, right? This is a really simple one. What is the weight here? Well, it's double this and add this. That's what y equals, right? And we looked at another example that's more like economic in terms of trying to find the weights that would predict the price of the housing. Remember, this is all a bit of review here, and we found out that the perceptron does that pretty well by basically finding out the weights, adding the bias term, and again, flipping that circuit on and off. You're exactly right. It's going to find a linear decision boundary if one exists, but it's going to find one. Right? And we don't have to get into the math today, but remember, it's basically looking at the bias term being completely at 90 degrees from the weights. And that's what's going to give you your best fit line. But as Ned says, it finds one, and hopefully that's the right one. And so we might run the perceptron numerous times, and the perceptron convergence proof tells us mathematically it will find a solution, but it does not tell us that it is the best fit solution. If we wanted a best fit solution, what's a similar kind of algorithm that we could deploy that would give us the best fit line? Say it loud, like with some basic, yeah, you're exactly right. Support vector machines. And the last thing we're going to cover today, just in review, is that when we do this on images, we're reading the pixels into this large chunk of this large array, where every pixel value is just a value that's separated basically by a comma, right? So you get this large vector of numbers. You see it's reading in there. Any questions in review before we jump on? You actually have it all together. Yeah, we talked about one thing the perceptron can't do very well is classify nonlinear stuff. And neural networks are going to allow us to do that. So questions? Hi, let's run into it. So again, the perceptron slide. Why is this slide always here? Because one way I like to think about this is that when we look at neural networks, right, we see these big confusing kind of flowchart things. Keep in mind that there are neurons there. And the neurons are doing very simple things like the perceptron. They're making basically a binary decision. We'll call that a logistic regression. Turn myself on, turn myself off. If I turn myself on, I send it down the line. One way we can think about this is like it's a giant factory. And you can't ever go inside the factory, but let's say that factory is really good at predicting faces. Right? You walk up to the front door, you knock on the door, you say, hey, I got a face, like a big boss meets you, and he goes, oh, I'll take a look at that. And then he takes it back inside, and what does he do? Well, he has like a row of neurons at the very beginning. And typically, in a classical neural network, each one of those input neurons is going to be 1 pixel. So if you have a 28 by 28 image, how many pixels is that? 28 by 28? Somebody might need their phone and a calculator. Yeah, what is that? Yeah, what is that?
20, whatever, 28.
Oh my God, somebody pull out their phone. It should be like 764 or something like that.
Times 28.
There we go.
What'd you say? 784.
784, okay. So you'd have 784 neurons right here, right? And imagine in that factory there are 784 desks right there. And you take that image and you read it as a bunch of pixel values, and then you give a pixel value to each desk. And then they look at it, and they're a little perceptron. If let's say that there's light hitting the matrix there, they decide to pass it on, right? And what we have in the middle here are these hidden layers, and these hidden layers are going to try to start to group together pixels into these low-level features, these corners, these edges, these loops, these things like that. And then based on the number of, you get to control how many layers you have here and how many neurons you have. And that's the whole art of making neural networks. You get to decide, based on the problem here, how many hidden layers should I have, what should I do in between the hidden layers, and how many should I have kind of in vertical columns. But basically, because we've given it a bunch of training data set, it's going to start to basically have some of these neurons pick out salient parts of the image, or the economic data if we're not working with images. And each one of those neurons is going to become kind of an important feature or a series of important features. Does that make sense? It's okay if it doesn't, because this is kind of high-level stuff. So you'll see that our neuron looks a lot like the perceptron. We multiply each input by its weight, and then add a bias term, and then squish that output from like 0 to 1, right? 0 means it's off, 1 means, okay, fire that neuron, keep on going. This is why we cover the perceptron so much. You'll see that there's one, like literally this is it, like I'm multiplying all the weights by the inputs, and then I get something that's like 0.086, and then you see this little alpha term. That's our activation function, right? And we actually have a function that does that. So for a long time, we used a sigmoid function, right? So we put it in, and now we use something called a ReLU. And basically what this is allowing it to happen is this is the function that if you cross that threshold, now I get to fire. Does that make sense? So in the literature, when you're reading about different neural networks, because you decide you need one for fish counting or looking at BiteTrack or YOLO, and you see things like sigmoid and ReLU, and sometimes they happen, sometimes they're documented in some of the model architectures. That's what you're seeing. This is the function that lets us know whether if the neuron should fire and then send it on to the next layer. Does that make sense? Questions about that? All right. You had asked, I think, Jack, you had asked about like ReLU and sigmoid a number of months ago, and I was like, just hold on. Does it make it more sense now?
Yeah.
All right. So what does this look like? So let's say our input digit is a 3. We're going to hit, these middle hidden layers are kind of trying to figure out what makes a 3, or what makes the entire data set, right? This comes from the MNIST data set, so it's like a bunch of handwritten numbers, and then has labels. And you feed all of this to the neural network, and it begins to break these middle hidden layers into salient features for the entire training data set. And then depending on how they're activated, it can try to make a prediction about what that number is. So here it's saying, and the thing is that we don't actually know exactly, you don't know, you can't look inside the neural network and say, oh yeah, that's the loop neuron, that's the horizontal neuron, but this is more or less how it puts it apart. It's going to say that, 0 has has a lot of horizontals, right? It also has a bottom curve and a top loop. Okay, so we take all of our 784 pixel values, we fed them in, we hit a bunch of horizontals, we pass the activation function because there were a lot of them and they summed to larger than 1. Okay, then we moved on, and as we moved on, we also found that in this image, there were a ton of loops at the top. If you put those two together, then you have a 0. Does that make sense? So it's like a bunch of perceptrons that are working at the same time in an order where you can pass forward. So we have that image at the factory, we give it to the front desk, and the ones that have a pixel value there, they pass them down, and they pass them down to the next level of desks. And let's say some of the desks begin to become, they've been shown thousands of images of faces before, right? And some of those desks get really good at like kind of telling what a nose is, right? They can't tell you exactly what a nose is, but they say, it's more or less in the middle of the face, it's kind of nosy. And if they get a series of inputs to that desk that look like a nose, they pass it on, right? And then some of those desks do eyes, right? And they know that eyes should happen right around here. And if they see 2 eyes, they pass it on. And then at the last, then you have this other level of desk that takes that information and goes, okay, I see 2 eyes and I see a nose. We're starting to look like a face, aren't we? Okay, awesome. And so then it goes to this last level, and they look at all of that, and they maybe ask the desk, okay, you see a nose, you see an eye, okay, it's a face. And then they tell you, then the boss comes back to you, the door opens back up, and he says, oh yeah, that's a face. You say, that's not a human face, that's a dog, right? That's the role that you have in terms of training data set. This is how the neural network begins to learn the proper weights and the proper associations of the hidden layer to actually have some knowledge that it can use again and again. Sound good? Do we have any questions? It's kind of highly theoretical stuff.
Wait, can you go back 1 second?
Yeah. It's going to run through a couple examples here. Yeah.
So like, input is 784 pixels.
Mm-hmm. Yep.
And then hidden 1, is that number below it? Is that the number of pixels, or is that like? I see that
yeah.
it's like consistently like decreasing, and it's giving like the best.
Yeah, you get to decide. We're going to look at the end of class of a bunch of different real-life architectures. This is just a demo, and those numbers at the bottom typically represent how many features you're bringing together, and we'll look at some examples that I think will make it more sense. Yeah, exactly.
What is the difference between the threshold and the activation function again?
The threshold is what you set the activation function to have to pass before you move on. So if you say a threshold is like between -1 and 1, or 0 and 1, right? McCulloch's artificial neuron, I think, was 0 to 1. The perceptron's -1 to 1. You get to decide what the threshold is, right? And then the activation function is what you pick as that kind of sigma or alpha to go ahead and make that prediction. That actually brings us right into softmax. So one other piece of this that you often see is these are really clear cases in which it's like, man, that's clearly a 0. But what if your neural network is taking a lot of training data in, and for whatever reason, it's often coming to solutions where it's not quite as clear, right? You have a bunch of different options. Softmax is just a way to try to take those, put them into a class probability score. It's 63% likely it's a fish or a dog, and then basically pick the one with the highest score and make a decision. Because chances are you don't have a bunch of different features in that image, you have one, right? And so softmax is basically a way that we're going to minimize lower responses and just make a decision. Does that make sense? And so we'll see softmax a lot in these bigger architectures because these are like critical decision points where you're like, stop just like hip-hopping around and make a decision. Is it a nose or is it not a nose? You think it's 70% sure it's a nose, and you think it's 20% sure it's an eye, we're going to treat it like a nose. So softmax does that. The way it does it is like very similar to the sigmoid function. It takes like the raw score and then basically applies a sigmoid function to it and then makes a prediction.
So softmax is an activation function?
No, softmax is a way of like, when you make a bunch of predictions, right? Softmax is a way of picking one that you think is actually probably the right one. Does that make sense? So let's say I have like 5 classes, and we're doing drone detection, and one of those classes is car, one of them is person, one of them is tree, right? At a given place, I think it's fair to assume that those things are distinct. You can't also be a car and a tree at the same time. And so if it thinks it's 30% chance that it's a tree, but 60% sure it's a car, because maybe from the top down that tree looks kind of car-ish, we're going to make it say, no, it's a car. Does that make sense? All right, so let's just go through and make sure everybody is on the same page here. We understand what a neuron is. What's a neuron?
It's a tiny function.
It's a tiny, yeah. What's an example of a neuron that we've covered quite a lot? The perceptron would be an example of a neuron that we've covered a lot, right? Okay, this is why we're doing it here. I feel like sometimes in lead up to the midterm, I felt like we weren't doing enough like vocab review, and so now we're going to do it. What's a weight?
It's basically just telling you how much like each feature
Input, how important it is. That's a really, really good definition. If you're not sure, Ned, can you say that again?
It's how much like each feature or like each input to the data set
Yep.
like affects.
And I have here it's learned during training, right? It doesn't know at the beginning how much is this feature more important than other features, but it begins to really learn to weight certain ones over others. The bias is just like an extra, if we can think about weights like you have a bunch of inputs for your problem, and weights, you get to turn a knob, basically it says how important it is. Bias is one other knob that you can turn at the very end to try to kind of dial it in. Does that make sense? Activation. We just covered 2 activation functions, ReLU and sigmoid. So if the combination of the weights and the bias term for your neuron exceeds your threshold, after you apply the activation function on, it fires just like a biological neuron. It says, let's go do it. I'm in pain, or I think this is a hat. Does that make sense? And then layers. These are layers. We got a layer here, a layer here, a layer here, and a layer here. We have an input layer and output layer, and then we have 2 hidden layers that are helping us make the decision. And we have a fuck ton of weights. I think in this we would have about 13,002 weights for this neural network.
So with hidden, like the hidden layers are basically just like during the training portion, they have just all of these types of all the data sets that they're training on, and they're basically just like minimizing like the outliers and just trying to put out the best.
Yeah, I think that's you get to decide how many layers you need, you get to decide how many neurons you have in the layer, and that's about what you get to decide. You get to decide your activation function and your threshold, and you get to decide what training data is representative of the real world task. And then it is going to learn, right, how to use those layers most effectively to solve the task, which is a little different than what we've been doing so far. This is sometimes why neural networks are considered to be a black box, right? Because you're basically able to give it the shape of what it is in terms of architecture and a lot of training data, and then it's going to figure it out.
So like you give it like what you want it to kind of like look at and figure out, and it's doing
You give it a bunch of instances of basketball players labeled as basketball players, and then you tell it, figure it out. And so forward pass is what's basically happening as it's flowing from input to output. And one thing that it does actually in training is it works backwards, and when it gets things wrong, it goes backwards in something called backpropagation to try to figure out how it should change the weights. And that's backpropagation is huge for neural networks. Backpropagation is the thing that's like very computationally expensive, and the reason why we went through like the AI winter of like 40 years. But now we can do it. And then the MNIST data set, that's that image data set that I kept using, again, the handwritten ones. All right. So we have a basic idea of what a neural network is, kind of the vocabulary that we're going to need. Now we're going to actually look at how do they do this pretty crazy, complicated thing of learning. And it's through something called backpropagation. So it goes through the hidden layers, then we have an output layer. And this loss function, that's basically when it's training and it says, definitely a dog. And you say, no, that's a cat. That's a loss for it. And now it needs to go back through the neural network and try to fix it so that it can make the the right prediction, which is why a neural network is only as good as its training data. If your training data is mislabeled, if you don't have enough training data, if your training data is based on some kind of bias that you're not aware of, say we're trying to do people detection, Nokia, we talked about this a lot, and we just use males, well, we may have trouble detecting people with longer hair or with quote-unquote more feminine features. Could be skin tone. It could be that we do dog detection, but our dogs are always centered right in the middle of the image because we pull them off of social media where people tend to center our image, and we give it to the neural network, and what those neurons actually learn is like how to detect the center of an image, not what a dog is. Maybe we're doing dog detection and we go through and we get pretty lazy labeling stuff, so we only label like 1,000. Would we really need like 10,000 per class? And what it gets really good is predicting your dog. But it doesn't generalize to like Copper, who's much different than Echo was, right? So we need a lot of data because the more data we have, well, one, the more features we'll have, and the more we can get refined in terms of the hidden layer doing its job, and then the more times we'll be able to kind of, in training, get a good loss function that can then go back and say, hey, that knob was here, that knob is here, that was really wrong though, let's back this weight back a little bit, let's change this bias term. Just like the perceptron learns, we're going to do the same thing with backprop. Questions, comments, concerns? So we initialize the weights for every single neuron and every single input just randomly at the beginning. The neural network has no idea. It just takes a wild guess. And then we start feeding information through the network, through forward passes. Then we measure the cost. So we compare the prediction that the neural network makes with our actual data that is labeled. Then we compute the gradient. We've actually covered this before, and we're going to do a little review. But the gradient is basically we measure the distance of error, and then we try to get the best. Try to get to the bottom of the bowl. You're shaking your head. Do you remember this? Yeah. And then we take a step downhill to minimize our loss, and then we repeat it again in little mini batches until we have like a lean, mean, sleek fighting machine where our loss functions are minimized. All right, so at the beginning, just absolutely random. After, if we put in the input digit 5, hopefully we get a stronger response at the final output layer than this like random stuff at the beginning. Pretty simple that way. Again, we've covered minimizing loss functions before in this class. We did this is why you're shaking your head. We did a very simple one where it's just like, how many hours do I put in relative to my grade? And we tried to like draw a little line that would give us, a basically linear function that could be useful. When we did that, we were taught, or we were reminded that one way to see how accurate our function might be is literally to measure the distance of error between our best fit line. Support vector machines do something kind of similar, don't they? How do they do something similar? The distance. Yes, absolutely. So this is really, really review stuff, right? We know this, right? This point here is pretty far off of our best fit line, right? So we have a pretty big loss between our best fit line and that data point. And a neural network is kind of the same thing. Our training data tells us that it is a 5, and yet the neural network makes a misprediction. Well, we can measure the distance between the predicted label and the actual label and classify that in a similar way. Kind of cool. Also not rocket science. And we'll do some things like squaring the gap. Squaring your error does two things. The larger the error, you get like a more exponential loss, right? So if the error is 8 and you square that, that's 64 versus 2 and 4. So you get like a higher response for really bad guesses. And then it also eliminates you like swinging too far back and far, because if you made 2 subsequent guesses, the neural network did, and one of them was negative and one was positive, they might cancel each other out and start to look like there was less error than there actually was. So as we took in that really simple example, right, we measured our function, our loss function. This is the one we did before break. We'll see that it begins to approximate a curve, right? A loss curve. This took me, for some reason, like I never could understand what they meant by a loss curve until I like wrote a thing that literally did it for me. And I was like, oh yeah, shit, it is a curve, right? And so when we're training a neural network or an algorithm to be a lean, mean, fighting machine, we probably want to be at the bottom of that curve, right down there. And the question is, how do we get down it? Do we just like move, we'll say we take 100 guesses, or do we say we'll take a guess, then compute the loss, and then take another guess? This all has like performance considerations, right? We want to do this as quick as possible. So we got to have a learning rate. And if the learning rate is too big, then you might be jumping all over the curve. That's what we see here. If it's too slow, well, it's too slow, right? This is important because when we train neural networks or we train deep learning models, it's very expensive. You need like potentially these GPTs that you use they're billion, trillion parameter models, right? So think about all the different neurons you have in there. And the cost of training is like, I think OpenAI only released the first 2 costs, and then after that they were basically like, no, we're not going to tell you, because if we tell you how expensive it is to train these, you probably will have some serious concerns about our economic viability. So being able to minimize this is important. If you have any chance to do it on your computer or the computer we have in there, our learning rate has got to be just like dialed in. Otherwise, it might take years to get to a good solution.
This is a more like specific question, but I assume you've probably seen stuff with like Anthropic and like U.S. government and stuff,
Yeah.
DOW. But do you think that Anthropic like has to tell like the government like what their cost error is? I mean, I would assume so, just because of like, you know, if you're doing that kind of work.
No, I think generally we're not beholden to tell people, even in peer-reviewed stuff, we usually are required to tell them what hardware we trained on, what our batch size and learning rate were, and then what our errors were. But usually, like, I don't report it took me 90 hours to train or 10 hours. But some of the, like, even what I would consider to be simple projects, like that are like entry level, which is right where we're at, are going to take you like a day of training on that laptop, right? And so we're gonna worry about learning rate. We're gonna learn about batch size, all these different kind of parameters that we can turn. But I think to answer your question more directly, this is like, you know how people like don't really even know how much energy one of these things takes? That's because they're not required to release that data, right? Because it takes, like I said, Backpropagation is what created the AI winner. This stuff here was so computationally expensive to do that it wasn't until modern big graphics cards came out, GPUs, because they excel at like basically linear algebra, that we were able to do it. And that's why like GPUs are so expensive. Bitcoin mining is similar. And if it took us like that long to come up with the technology, it's probably safe to assume that it requires a lot of resources. So yeah, gradient descent is like just a smart way to try to go down that curve and find that local minima. Boom, right? So we're taking steps and we're calculating each step. You see how the steps get smaller as we get down to the bottom of the bottom of the curve. That way we're not like shooting up the wrong way. Pretty cool, pretty simple. Let's make it a little more complicated. So we can see what this looks like in more than one dimension, right? And this is what I think is trippy, is like we're seeing this in kind of a three-dimensional space, but dimensionality is something that's hard to wrap your head around. I mentioned earlier that like there would be like 13,000 weights approximately in that simple neural network. It means you're working in like 13,000 dimension space. So we literally can't, I show it in a 2- and 3-dimensional space because you can see it, but we're trying to do something similar. I just don't think we can really represent it in our brains in a geometric way. Okay? So we want to find the lowest values. And the true landscape for most neural networks is millions of dimensions. But we're maybe a geometric representation there is no longer helpful, and we just need to rely on some algebra. So we want to minimize our cost function. We want to minimize our loss. And we also want to make sure that we train the neural network on good data that is actually, a fish if we say it's a fish. But we don't want to train it on all of our data. We want to hold some of our data out. That way we can test it at the very end and see if it actually does its job before you ship it off or you say it's good to go. So it's a 70, 15, 15 training and validation set. And we started to talk about like all these different knobs. We have activation functions, we have thresholds, we have learning rate. We're starting to get a bunch of what we call hyperparameters. And what the validation data set does is after we have a good one, it basically runs through a bunch of different hyperparameters to make sure that you've kind of picked the right ones. And then once we have that done, we go ahead and test it on some of the data set that we've just left out. We talked before in this class about sometimes we'll use a k-fold cross-validation, which is like shuffling the cards and then putting them into piles. We'll do that when we really need to make sure that the data set is completely randomized. What would be a real-life case example in which you're going to build a neural network, throw a bunch of label training data into it, and you need to make sure that it's actually randomized? Face detection, yeah, we talked about that. Let's say, trying to think of different projects. Yeah, let's say that you're gonna label these salmon, right, from the drone imagery. Let's say that like Fish and Game wants to do this, and they're interested in the product, and we did all of our data collection on a Skydio X10, right? But let's say there are like 20 or 30 different drones you could use. And what we have is like 5 million images of fish from a bunch of different drones. There could be things, the low-level camera parameters, focal length, the way that the reflectance values for that camera work, all those things that we covered already that are different between the drones. And you wouldn't, if let's say the way that we assembled the training data set was literally I sent emails and people sent me data and then I just added it again and again. Well, maybe what we get is like the training data set over-represents the drone that I used and none of it's in the test data set, right? So then what the neural network, because remember the neural network is just figuring out what knobs to turn and then comparing it to the labels. Maybe it starts to just develop an algorithm that can detect the actual drone aircraft rather than the fish. I did this a number of years ago, trying to design a neural network to detect small vessels. And it was like an idea I had for search and rescue after I got back from Alaska, so I hadn't collected any data. But one of my friends, who's an archaeologist, we were going to all these sites and using like a drone with a multispectral sensor. And then he had like a little DJI, and he'd always do like, he's just a drone guy, so he'd just like make little cool videos. And in the videos, there always was the boat that we came in on, right? And I was like, oh, I can just take those videos, I can cut out all the stuff that doesn't have boats, I can take the video and turn it into images, and then I can label those images, and then I can feed them in the neural network, and I'll get like a good, efficient algorithm for detecting boats. But since he was doing cinema stuff, he was always like, when he decided to look at the boat with the drone, it was always completely focused, it was always in the middle of the image, it was always centered. And so when I took that training data set and I tested it and I did all that stuff and I tried to put it on other images of boats, it never worked. It just couldn't predict them. Now, what it could only do is predict a similar type of boat, because we were using the same boat every time, so there wasn't a lot of variety there. It could only detect that type of boat when it was in the middle of the image and there was like a pretty sunny day, because that is the training data set I put it on. Does that make sense? Yeah, you gotta head out. Let's take like a 5-minute break, and let's keep rolling, then I'll let you out a little early. Yeah, I wanna get some water, but the other thing we might need to really worry about is how much can we feed in. Some of these data sets are huge. They're like GPTs are trained on web crawl, which is like 20 years of the internet. Wikipedia, Reddit, like anywhere, it's massive. Some of the foundational models that we use for image detection need at least 10,000 labeled images per class, right? And if you feed that all into your neural network at once, well, you have to wait a while before you do that cost function stuff. So instead, we might, just similar to the K-fold, we might split our data set, our training data set, into little batches. So like pick 32 random samples is one batch. And we get to say what the batch size is. Is it 16, 32, 128? And we usually do that based on like what our computer can handle, right? And then we process that little batch, and then we do the gradient and do our loss function. That's something, as we start playing with this, batch size is one of these hyperparameters that you are going to get to control. Questions, comments? So there's a trade-off between the full data set, medium batch, and then something called stochastic gradient descent, which as our batch size gets smaller, is really quick, but you have a smaller sample, so you might be kind of just all over the place. I want you to imagine you are standing at the top of a hill, like in the Blue Ridge, where they've just gone through and they've cut all the pines out, right? It's like logging, right? And you're standing at the top of the hill, and you basically can envision a topographic map on that hill. And what we're trying to do when we minimize the loss function is like try to get down that hill as fast as we can go, right? And that would probably be moving down just the steepest parts of the hill. Because if it's not as steep, well, the distance is going to be longer to get down to the bottom. And so what we're going to do as we're standing on top of that hill is that with batch sizes, what we're kind of deciding is how many steps can you take at a time before you kind of re-look at where you are, right? If any of you have ever been like in ROTC or done orienteering with a compass, has anybody used a compass like in Boy Scouts or something like that? You try to figure out where you are on the map, then you take a couple steps forward, and then you kind of have to re-measure. The batch size is like how often are you re-measuring? Make sure that, yeah, it can be a little quicker that way. You have to wait as long before you remeasure. But a really small batch size might take some time too. So stochastic gradient descent is that metaphor where we're at the top of the hill. You're trying to be very specific, right? You're like, I'm going to use math, and I'm going to like get on an app. I'm going to see where the topo curves are, and then I'm just going to walk down the steepest part of the topo curves because I know that will get me down there the quickest in terms of the distance I've covered. Stochastic gradient descent is where like I give Bass a bottle of whiskey, he gets really plastered, and then he goes, I'm just going to go for it, and he walks down, right? Why would we do that? Why is stochastic gradient descent is something that we see all the time with neural networks? It's faster, right? And so he's down at the bottom. He's like, hey, I made it. And you're still like, I can't find the app that's got like the right topo contours, and I'm still trying to download it. That's exactly why we might use stochastic gradient descent. It might be why we use batch sizes too. It is just going to be quicker. And at the end of the day, this is a little diagram of like, it's trying, this is the drunk one. This is the true gradient, and it's just going to try a bunch of different things really quickly and then average them up, and you get something that's almost the exact same. So that's the perfect loss function, and stochastic gradient descent is a little more messy, but we get there at the end. And at the end of the day, if our loss function is minimized and we are accurately predicting our labeled data, and our labeled data is like actually useful in real life, then who cares if we went to it really noisily or if we took the perfect little steps on the way down. We just need it to be fast because training data takes a while, and we want it to be as quick as possible. So we're going to shuffle our data with something like k-nearest neighbors. We're going to pick a small segment of that data. We're going to pass it through our network. We're going to compute the costs. Then we're going to do that back propagation where we decide what is actually right, and then we're going to update the weights between each neuron. Make sense? Let's just take a little time here. How confusing? Fist to 5 means I get this. This is pretty easy. Fist means I'm pretty confused. Where are you at? 3? 3. You're at. What's hard for you right now? It just kind of doesn't make sense. What about it? Because you talked about using convolutional neural networks, right? Which is exactly this.
All the words.
I'm hitting you with a lot. Okay.
I think like seeing this in my own project would make it a lot clearer.
Mm-hmm. And some of us might not use this in their project, right? Some of us definitely will, though. So again, we're going to start our neural network, which is made of a bunch of perceptrons. It's just random. It doesn't know. We're going to feed data through. Astrid, for you, that's a bunch of like labeled instances of snow. Snow or no snow. These are 1,000 images that have skiers in them. And I've drawn a little bounding box around the skier. We're going to pass those through those input layers, the hidden layers, and the output layers. And at the very beginning, it's just going to say, skier? And you're going to go, holy moly, no, definitely was not a skier. There's no skier there, right? You made a huge error. Measure the cost of that error. And it's going to say, oh yeah, I was way off. I thought it was 90% sure there was a skier, and there was actually no skier. Okay, cool. Now minimize that with back propagation. Go back through the network the other way and turn whatever dials you need so that at the end of the day, when you see that thing again, you know that there was no skier, right? Do that a lot. Do that over a day and a half of the computer just on, going. In fact, do it so much that instead of looking at the entire data set of my labeled skiers before you do steps 3, 4, and 5, start doing it like every 32 images, right? That would be batch size. Does that start to make sense? Get to a place where when I show you something out of the training data set, you are like positive that there's a skier when there actually is. And as long as your data set is then representative of actually what it looks on the mountain, your neural network should perform very well. Does that make sense? Okay. That's what a neural network is. There are some problems with that approach. So we now often use what's called a convolutional neural network. Okay, so let's go back to the MSIT data set. Remember the first layer of neurons in our neural network? How many were there? There's 764, because the MSIT data set is a 28 by 28 pixel, right? And every neuron at the beginning just looked at one pixel, just one pixel. Well, that means if you have the same image, like literally this is the same 3, I've just shifted it over in the image 3 pixels. If we're only looking at single pixels, then we're going to get to a solution where they are treated like different numbers even though they're the same number. Does that make sense? I don't know why this is not, sometimes the things that I have on my computer don't show up well on the projector. Must be like an additive color problem. But if we're only looking at individual pixels, we shift this 3 pixels over, then that pixel that used to be really dark and say that it was on, now no longer is on. So what we need to probably do is kind of group it into regions and not be treating every pixel differently, right? What we need is like little small patches. Hey, we know something that already does this. What is it? Kernels. Yeah, kernels. We could, instead of having a bunch of individual features or neurons at the very beginning, we could design a kernel to extract some features and then treat that kernel as kind of a region. So we're going to, and this is something we should be very familiar with, right? So we got a 3x3 filter, and we're taking the input, that filter is a 6x6. We're going through, and we're building a new output that is kind of the regions of interest grouped together as one, right? This is new to us, or not new to us. It's something we should be very familiar with. Now maybe if our neural network is kind of takes a large part of what it does is it convolutes over the image and kind of groups things, well, now we might have a more accurate type of neural network. Does that make sense? So just a little review. What do filters detect? Well, this one does horizontal, that does vertical edges, this one blurs. We might throw a ton of different, like every layer of the hidden network might be a different type of feature extractor from a convolutional kernel, and then that's what we end up twisting our knobs to decide if it's good or not. Does that make sense? We're combining like some very low-level feature stuff with this neural network, and we might get to something that's super scary accurate. And what's important here is that we're not actually designing the kernels. In our neural network, we don't say, oh yeah, use a Sobel filter and then you use a blur. We basically say you're a neuron that is going to figure out a kernel that extracts features that are useful for you to make the predictions that align with the training data. That's kind of cool. That means that if we're running like 4 or 5 filters over a given layer, that the output of it is typically going to be smaller, right? Because if we're averaging values, you get like a smaller kind of image, so to speak, but there might be a bunch of different dimensions. So here there's like 6 dimensions from that neuron. So this is why we spent so much time talking about if there's a matrix of light and it's in colors, it's 3 dimensions, right? And so now we just might have more than 3 dimensions. The other thing that we'll do in convolutional neural networks, which is a little different, is as we're convoluting, sometimes we'll get a bunch of responses together in kind of a, I'm going to draw this out. We'll get a bunch of different responses together, and just like softmax was supposed to pick the one that's the most probable, max pooling, if this is the result of it, the result of your convolution over the filter shows you this. All that max pooling does is use this. Use the 9, it's the biggest. So we're literally just pooling it together. So just like we saw in the traditional neural network, we have different layers and they have like features. We're just extracting features from kernels now, and we might do some max pooling at the end to pull out the features that seem to be most important, or the values, the pixel values that seem most important. So we have convolution kernels and we have max pooling now, and those are kind of two more things that we add into that neural network architecture. So I have an input, 28 by 28 pixels. That's our MSET data set. Here, for example, it says a 3 or 4. Then we're going to convolute over it with a ReLU activation function. And you notice how this becomes 6 now? Because we are basically running 6 filters over it, right? Then we're going to go through those 6 dimensions. We're going to max pool. We're going to say, give me the maximum values that got returned. Those would be your strongest edges or your strongest corners or your strongest diagonal edges. Okay, now do that shit again, right? Do it actually on a smaller segment of the image. And then what do? Max pool that again. Flatten the image, and now make your prediction. Does that make sense? So what's different from the neural network? First, we're convoluting on the image. Second, we're doing some of this feature extraction from filters now with kernels. We are still using ReLU traditionally as an activation function, and now we have this max pooling thing where we run the convolution, we get our values. If they're activated, great. In order to decide whether we're going to activate or not, we'll take the max pooling, like the highest response from that given convolution. So I really wanted to get to this and give us plenty of time. That was a lot. I know it was a lot. I know I dropped a lot on you today. Let's look at some examples. RCNN, one of the first types of convolutional neural networks that could classify images almost in real time. So you could use it on a phone, you could use it with a video feed. How does it work? It takes the input image, and first of all, it uses a resizing kernel. We talked about kernels can be used for resizing, like bilinear, bicutic interpolation, and it resizes the image to this, right? 3, do you think it takes color images? And then it goes through, and first it runs a convolutional 5x5, then a 3x3, then a 3x3, then a 3x3, and then it goes into fully connected layers, like the neural networks that we just talked about at the very beginning of class, where we're not convoluting, and it does 3 of those. And at the end, it gets to something that's pretty accurate. This is an example of how these RCNNs are often used. This is classifying satellite images. So you could have a bunch of baseball fields labeled, a bunch of track fields, a bunch of ocean liners. As long as you've got them labeled in the image of where they are, we go ahead and we put it through our convolutional neural network, and then we can get a prediction with a confidence score. I think it's 60% sure that this is a tanker moving through the Strait of Hormuz right now, of which almost none of them are, right? YOLO. This is something that a lot of you mentioned in your midterm. I'm going to use a YOLO, which usually I almost always agree with you. It'd be a great algorithm to use. It's first invented in 2016. YOLO is really, really fast, which is why you see it so much, and why YOLO is used for things like detecting drones and FIS images. And also why it founds usually the backbone of what ByteTrack is doing. What are we doing in YOLO? Well, we're starting with a 7x7 kernel, right? It's sliding over the image. Then we have a 2x2 max pool layer, and then we have basically different convolutional layers with a max pool after every time. And then we have 2 connective layers, which are similar to the first type of neural networks we had. You see how you get to decide like how many hidden layers do you need here and how big should the kernel be? That's what the architecture design, this is what people get paid a lot of money to do. Now, thankfully in this class, I'm not asking you to make any from scratch. You just need to identify which ones might be useful. I think YOLO will be useful. And I say, good to go. I'm going to help you write some code to do it. So YOLO is fast. It's really easy to use. It's edge compatible. You can use it like on a cell phone. It's really lightweight. It takes a lot of resources to train the thing, but to actually deploy it, not that much. And what it's doing, this is directly from the first YOLO paper, what it's doing is it's giving a lot of confidence scores of where it thinks things are, and then having like a class probability map and basically suppressing bounding boxes that don't have the highest confidence score. Kind of similar to what Softmax was doing. Object tracking, I think both Manning and Ned have discussed this might be something they need to use. This is like a whole pipeline. We have the input video, we turn it into images. We use an object detector like YOLO here, and then we basically pay attention to where that bounding box was, compare it back to the video frame, and see how the bounding boxes are moving. So ByteTrack does exactly this. It takes an input object detector you choose. Most people are going to use something like YOLO, and you have all these different bounding boxes, and it looks to see how, 0.09, 0.09, it's pretty positive this is a lady, and it's basically trying to track how is that lady moving through the frame. Pretty simple stuff. Pretty simple stuff. So using something like ByteTrack is going to be, in total, maybe 10 lines of code. These things are maintained, they're open, they're free to use. What might be more difficult is figuring out what data you want to bring to the equation and how your data set is going to be representative and whether you can actually accomplish that this semester. Instant object segmentation is another classic thing we do with neural networks. So we have a bunch of real world images. We label them. This takes a really long time. We have our training data set. We go ahead and put it through, and now instead of a bounding box, we have like a perfect little segmentation mask, which can be useful. Sometimes you don't want a box around that thing, you want like an actual pixel by pixel mask dropped over top of it. U-Net architectures are another type of convolutional neural network that we use. These are mostly used in satellite imagery, basically times where you have to pick out very small features. So this is a leaf that has some blotting on it because it's unhealthy, and what we want to do is draw a segmentation mask right around the unhealthy parts. And then we could classify not only that we can find the blotches, but then we could like subtract the volume of these blotches from the image and have like a proxy of how healthy or unhealthy the plant is. You could use this for looking at like fertilizing corn, right? What are the areas in which there still isn't really healthy vegetation? Same type of thing. U-Net is called U-Net because it looks like a U. But again, we have a bunch of convolutions. So those are small filters out of 3x3 that are activated from ReLU. We have a lot of max pooling. That's basically it. It's a combination of different types of basic design principles that we've covered already. Any questions? I know that's a lot. We have about 10 minutes left of class. I want to know what questions you have and how I can answer them, and it's totally okay